This is Lecture 10, the first of 2 lectures on calculus. Again, I am not going to attempt in 2 lectures to teach you the calculus you would need for a college calculus course. The whole idea is to introduce you to the notion of why calculus is important, the historical development of calculus, and the applications of calculus. In this lecture, we'll talk about the derivative, the key to calculus. By the middle of the 17th century, there was a significant demand for mathematics of change to be used in the analysis of new scientific discoveries. Among the discoveries was the investigation of the motion of the planets within the field of astronomy. And the movement of the planets was highlighted by 3 laws written by Johannes Kepler. His laws of planetary motion demanded mathematics beyond that of the linear function, where change was happening at a constant rate, to new situations where change was happening at a changing rate. In 1665, Isaac Newton created what he called fluxions, which was a method for finding the rate of change at any point on a function. Newton kept his discovery a secret to all but his closest friends until a rival was about to publish a similar work. In 1673, Gottfried von Leibniz published his work on the calculus. Leibniz's work was widely praised in Europe due to his popularity. Newton was a cold and aloof individual, and Leibniz was very sociable. In fact, he was considered a ladies' man. In today's terms, he was a party animal, while Newton was exceptionally unfriendly to all but his closest of comrades. In fact, one of his friends, named Halley, after whom Halley's comet was named, was the gentleman who caused Newton to publish his book on fluxions, because, again, he was afraid that Leibniz would receive all the credit. Newton, in fact, believed that Leibniz had studied his works, that is, Newton's works, and stolen ideas from Newton's works. And basically, Newton, because of his tremendous stature among the scientists and mathematicians in England, prevented Leibniz from getting credibility in terms of calculus in England. And in the English-speaking world today, when people think of the creation of calculus, we talk about Newton. In the rest of the world, we talk about Leibniz. The interesting thing is that most of the notation we use in calculus today was first written by Leibniz. We do not use Newton's notation. The foundation of both Newton's work and Leibniz's work has to do with the concept of limit. And it really is important, because without understanding what a limit is, the rest of calculus is quite difficult to understand. The limit of a function of x, that is, x is what determines the function, as x approaches a specific value, can be conceived of as the value that the function appears to be approaching, even if the function never reaches that value. In other words, as you get closer and closer and closer to a certain value of x, what is happening to that function? How close can you get? What I like to talk about is a thin salami slice close. How thin a salami slice? So thin that you can't see the salami, but you can smell the garlic. And if you're that close, you can look ahead just a short down the road and see where you're going. You may never get there. We'll now use the TI-83 to look at one example of a limit where it's apparent where you're going, and when you get there, you're not where you thought you were. And here is the graph of y equals x squared minus 9 divided by x minus 3. If we use the trace button, we can begin to look at the values of y as x approaches 3. You'll notice when x is 0, y is 3. Let's take a look what happens when x is 2. When x is 2, y is 5. How about when x is 2.9? When x is 2.9, y is 5.9. We're approaching 6. It's obvious we're approaching 6 as x approaches 3. We get closer and closer to x equals 3. Y gets closer and closer to 6. But what happens when we reach 3? When we reach 3, y is blank. You'll notice there's a hole there. There's a gap in the line. And the reason is when x is 3, we have 0 divided by 0 if you replace the x in the equation with 3. And therefore, we cannot graph a point. That particular location, we have an undefined value of y. This is called an indeterminate point. And therefore, although the limit as x approaches 3 is 6, when we get to 3, there is no value of y. That does not preclude the limit from being 6. The limit is the value of y as x approaches a particular value of x, even if the function really doesn't get there. Using the concept of limit, we can develop the derivative and then investigate the derivative of various functions. Our function is defined as y equals f of x. Simply means that we can determine y when we know x. And we choose 2 points on that function that are very close to each other. One is at x, the other is at x plus h, where h is a very small number. Now, in our graph that you see, it appears that h is quite far away, but we're actually looking through a very powerful microscope. Perhaps in this microscope we can actually see that thin salami slice. The 2 points that we've selected on our graph can be represented by ordered pairs. The first is x comma f of x, y equals f of x, and the second point is x plus h comma f of x plus h. We can now draw a line segment between the 2 points and find the slope of that line segment. Remembering we can always find slope if we have 2 points. It's the change in y divided by the change in x. So we have our slope, m, equals f of x plus h minus f of x, the change in y, over x plus h minus x, the change in x. And therefore, we take this particular line segment and we make h smaller and smaller and smaller until x and x plus h are almost touching. We still have 2 points, but they're microscopically apart. And the line segment between them has a slope very, very close to the slope of the tangent line. The tangent line is touching the curve only at the point x comma f of x. And now we can define the derivative, commonly written as dy dx, as the limit as h approaches 0 of f of x plus h minus f of x over h. Notice we have h in the denominator since x plus h minus x is h. So as h gets smaller and smaller, the limit of the slope of the line connecting the 2 points is the derivative, is the instantaneous slope at a single point on the graph. And since we have not told you what x is, this is true for any value of x on the function. So now we understand limit, and we've used limit to come up with the notion of the derivative. Let's see if we can take something that we already know the derivative of. You see, wait a second. We haven't talked about derivatives. How could we know the derivative? Well, we do, because we know about the derivative of a straight line. Before we talk about that, just so you will not get confused if you see the derivative mentioned anyplace else, there are various notations used for derivative besides the dy dx that we've already used. There's f prime, the prime being like an apostrophe of x, f prime of x. There's also y prime. There's dy dx, which we've already seen, and capital D with a subscript of x. All of those mean the instantaneous change in y as x changes. That is, the change in y with respect to x at a single point on the curve representing a function. So now let's take a look at a linear function. Y equals mx plus b, We know that it has a slope of m, and therefore the derivative, which is the instantaneous slope at any point, is m because the slope is never changing. So let's take a look at the definition of the derivative. F prime of x, again the derivative, equals the limit as h approaches 0 of mx plus mh plus b, that's f of x plus h, minus mx minus b, that's minus f of x, over h. The limit of that as h approaches 0. Well, of course, the mx cancels, the b cancels, and we're left with mh over h. The h's cancel, and we're left with the limit as h approaches 0 of m. But no matter what h is m. So therefore, our derivative for the function y equals mx plus b is m. We already knew that, but at least this shows us that this definition of derivative actually works. What we now need to do is to look at some common functions, look at the graph of the function, determine what the derivative should do or how it should act, and then see if the derivative does that. Let's go to the TI-83 to look at our first function. This is the graph of y equals x squared. It appears that the slope of a tangent line, that is the derivative, will be negative when x is negative, when x is to the left of the y-axis. And the slope should be 0 at the vertex when x is 0 because we have a horizontal line tangent to the parabola. And when x is positive to the right of the y-axis, our slope, our derivative, should be positive. So when we look at the derivative, it is important to understand that it should match up with these details. Well, we use the definition of the derivative to come up with the derivative for y equals x squared. And that derivative is 2x. That says take x and double it, and that is the slope of the tangent line at that point on the graph. Well, let's examine our situation. When x is negative, 2x is negative, the slope is negative. When x is 0, 2 times 0 is 0, the slope is 0. When x is positive, 2 times x is positive, the slope will be positive. So the characteristics of the derivative we saw when we looked at the graph of the function are met by the value we get for the derivative. The derivative of x squared is 2x. Let's take a look at a couple of more functions. Let's go to the TI-83. Here is the graph of y equals 1 over x. You'll notice when x is 0, there's no point on the graph. In fact, the graph jumps from below the x-axis to above the x-axis. That is because when x is 0, 1 over 0 is undefined. We cannot divide by 0. You'll notice that to the left of 0, for negative values of x, the graph of our function is going down. It's decreasing. As x gets closer and closer to 0, y gets more and more negative. What does that mean in terms of our derivative? It means our derivative had better be negative when x is negative. And in fact, as x gets closer to 0 and negative, our derivative better get more and more negative. At 0, since there is no value of the function, the derivative should also be undefined because we can't have a derivative where there's no point. And to the right of 0, the slope is also negative. That is, the function is decreasing. And as we get further and further to the right, the derivative is getting less and less negative. You'll notice to the extreme right of the graph, as seen, the slope is almost 0. It's flattening out. It never gets 0 because it never touches the x-axis. This is called an asymptote. The graph is getting closer and closer to the x-axis without touching. So to review, when we get to the derivative of 1 over x, it better be something that is always negative except at 0, where the derivative should be undefined, doesn't exist. And as we get closer to 0 from the left, the derivative should be extremely negative. And as we go away from 0 to the right on the positive side, the derivative should be getting less and less negative and approaching 0. We'll take a look at that in a moment, but first we want to go back to the TI-83 to look at one more function so we can analyze what the derivative should look like. Here is the graph of y, or f of x, equals x to the third. Notice that to the left of the y-axis, the graph is increasing. but it's increasing at a decreasing rate because as it reaches the x-axis, it gets horizontal for a brief second at x equals 0, and then begins to increase at an increasing rate. Hopefully you'll recall we call such a point where the rate of change in the rate of change changes to is an inflection point, because to the left of 0, the function is increasing at a decreasing rate. To the right of 0, it's increasing at an increasing rate. But we're concerned with simply the derivative. What is the slope? Well, obviously, the slope is always positive. This is an increasing function, except at one place, at 0. When x is 0, the slope must be 0. Furthermore, we see that for negative values of x, we should have positive values of the derivative, but those positive values should be getting less and less positive, that is, approaching 0, as x itself approaches 0. And to the right side of the origin, or the right side of the y-axis, our derivative should always be positive and be increasingly positive. That is, as x gets larger and larger, so does the derivative. So let's take a look at the two derivatives for these functions. The first function we looked at in this set was y equals 1 over x. And if you have a function, f of x equals 1 over x, its derivative, as defined by the definition of the derivative, is negative 1 over x squared. If you remember, we said that the derivative of 1 over x has to be negative every place except at x equals 0, where it's not defined. Well, is negative 1 over x squared negative for all values other than 0? Absolutely, because 1 over x squared, provided x is not 0, is always positive, and the negative of that is always negative. When x equals 0, is the derivative undefined? Absolutely. 0 squared is 0, and we have negative 1 over 0, which certainly is undefined. And notice that as we approach x equals 0 in our derivative, we have negative 1 over a very small fraction. And as x gets closer and closer to 0, x squared is becoming an infinitesimally small fraction. Well, the negative reciprocal of a very small fraction is a huge negative number. And recall we said that as this function approaches the y-axis from the left, our derivative has got to be negative and getting increasingly negative as x gets closer and closer to 0. On the other hand, as x becomes a fairly large positive number, negative 1 over x squared is negative 1 over a fairly large number. A large number squared gets pretty big. And negative 1 over a fairly large number is closing in on 0. It never reaches 0. Negative 1 over a billion squared is a very small fraction, but it's not 0. So indeed, negative 1 over x squared is the derivative of 1 over x in terms of the definition of the derivative, but more importantly, based on our graph of the function and knowing how the derivative should behave. F of x equals x cubed, based on the derivative definition, has a derivative of f prime of x equals to 3x squared. Notice that 3x squared is always positive when x is non-zero, because if x is a negative number squared is positive, and 3 times a positive is positive. If x is positive, a positive number squared is positive, and 3 times a positive is positive. The only place where 3x squared is not positive is when x is 0. And we said for the function f of x equals x cubed, at 0 we have an inflection point. We have a horizontal tangent, and the growth rate is going from increasing at a decreasing rate to increasing at an increasing rate. There is no question that f of prime of x equals 3x squared is the derivative of f of x equals x to the third. And that has been validated by our use of our graphing. Again, without Descartes, there wouldn't have been calculus because Newton wouldn't have been able to look at these functions. And without Descartes, we would not have been able to validate that Newton and Leibniz were correct in how they defined the derivative. We can now look at applications of the derivative in the real world. And again, many people feel challenged by having to take a calculus course. And usually the reason is their knowledge of algebra is not sufficient to allow them to perform the various techniques. But when asked why they should take calculus, if they're not going to be an engineer or these people are not going to be a scientist or a mathematician, there's a very good reason. Because through all this, we've talked about change. And to me, calculus is really the philosophy of change. How things change, examining that change, how the change is changing. And in fact, if life was not full of change, where the change was changing at different rates, life wouldn't be very exciting. So let's look at a few real-world examples. In business, we can measure marginal cost, marginal revenue, and marginal profit. The term marginal refers to the instantaneous change in cost or revenue or profit as one more unit of product or service is produced and sold. Why would a business person want to know about marginal revenue? Well, what it says is if I produce one more unit of production, how much additional revenue would I earn? Marginal cost would tell that person if I produce one more unit of production, how much would my cost increase? And most importantly, marginal profit would say, if you increase your production by 1 unit, here's how much additional profit you will make. So calculus is a vital tool in looking at business because typically most businesses are looking to either maximize profit or possibly maximize revenue, and in many cases looking to minimize cost. The change in the money supply is quite important. This is sometimes called the velocity of the money supply. Velocity is the rate of change over time. Or more correctly, the velocity is the derivative of a function of time. If you're looking at distance as a function of time, the velocity is how rapidly the distance is changing. So we talk about the velocity of a pitcher's fastball. It's simply a derivative. How is the distance from the pitcher's hand to the home plate changing as time increases? The velocity of the money supply is simply how the amount of the supply of money for the nation is changing, increasing or decreasing over time. Now, why is this important? Well, we are concerned with the analysis of this number, this derivative, because it is useful in looking at the financial health. There are many people who would say that if the velocity of the money supply itself was increasing, that is, the derivative of the derivative was increasing, that we are increasing at an increasing rate our money supply, and this could lead to inflation. On the other hand, if the money supply was increasing at a decreasing rate, that is, it's increasing but not as fast as it was in a previous time period, that might be reason to fear some slowdown in the economy. And obviously, if the money supply itself was decreasing, we probably have some serious problems, and it might even be too late. Again, this is a reason why the derivative of the derivative, sometimes called the second derivative, might be more important in terms of analyzing change than the derivative itself. We could look at sales or profits in terms of a company and look at the derivative to see how are sales changing. Are they increasing? Are they decreasing? Are profits increasing or profits decreasing? And the second derivative would tell us how the increase or decrease in sales or profits was changing. So, for example, I work for a company whose profits were increasing, but increasing at a decreasing rate. I was a new manager in the company and really had very little chance to input. And I guarantee you, based on what happened next, the top management of that company had not taken or at least understood calculus. Because looking at this, one would say if the increase in profits is increasing at a decreasing rate, what that means is that sometime we may have no increase in profits. And at some future time, we may actually have a decrease in profits. And in fact, 2 years later, this company was bankrupt. And many people, including myself, lost jobs. Many of those people should have known better. And had they recognized this, had they understood calculus, perhaps I wouldn't be standing here but still working on Wall Street. I doubt it. The derivative is vital in the world of physics. We have already mentioned the need for the derivative in terms of planetary motion, since we're looking at how rapidly the planet travels through space around the sun. And the velocity, again, the first derivative of that motion, and the acceleration, the second derivative of that motion, is quite important. And again, we refer back to Kepler's laws that talked about this motion, because it's always nice to know where a planet's going to be and how fast it's traveling and where it's going to be in the future if we're planning to launch a mission to that planet. Because if you aim your rocket at where Mars is today, by the time you get there, Mars will no longer be there. So you've got to know where it's moving, how rapidly it's moving, and the acceleration of that movement. The velocity is simply the derivative, as we said, of the distance function. And the acceleration is simply the derivative of that distance function. Physics, in many cases, deals with flux or changes in fields. Fields such as gravitational fields, electrical fields, and magnetic fields. And the derivative is used to quantify those fields. How is the magnetic field changing? This will affect the flow of electrons through that field. In fact, in your television set, you see a picture because the magnetic field directs a flow of electrons, which strike a screen, and the energy from those electrons cause little bits to light up with various colors, and you see a picture. Well, calculus tells us about the velocity and acceleration of those electron particles. There are laws of physics which deal with the conservation of energy and the conservation of momentum. So what that says, in a closed system, if two bodies collide, the momentum after the collision is the same as the momentum before the collision. The energy that existed in those bodies before the collision is the same as the energy in that system after the collision. Using a derivative allows us to measure changes so we can see that increases in particularly the momentum of one body, which would be a derivative, is balanced by decreases in the momentum of another body. So that overall in that system there is no change in momentum and no change in energy. In electric circuits and in electromagnetic induction, change must be measured. The derivative is the tool that's used to measure the change in the flow of electrical current and the change in electromagnetic induction. But the derivative is not limited to business and to science. And that is why I believe that almost everybody should take some calculus course just to understand about change. In the social and life sciences, the derivative is needed to measure change. Measuring population growth or population decline can be done if you can come up with a function that represents the growth of population or the fall off of population over time. The derivative would tell you how that population is changing, the rate of change. Changes in environmental quantities can be found using the derivative. Pollutants, carbon dioxide, carbon monoxide, nitrous oxide. We can come up with a function over time to measure how much of this substance is in the air. Looking at the derivative, we can measure the change. Obviously, if pollution is increasing, the derivative is positive. If pollution is decreasing, the derivative would be negative. And in fact, looking at the second derivative once again would tell us how the change is changing. Are we improving or are we getting worse? Changes in crime rates, in recidivism rate, that is the return of prisoners to prison once they are released, and in police effectiveness can be measured by creating functions, and then the derivative would tell us how these situations are changing. Not simply over time now, but also as we change, for example, what police officers are being paid or how we handle prisoners at various prisons. The differential equation is a means of creating a model to analyze the interaction between a measurement and the change in that measurement. When we have measurements and changes, we can use differential equations. Predator-prey analysis and models for epidemic use differential equations. The second lecture on calculus, lecture 11, will cover the integral and the power series.